Hey guys, how's it going? This is Lewis, and if you don't already know me, I study math and machine learning. I really enjoy explaining complex concepts in a way that's intuitive and easy to understand. I really enjoy prioritizing a deep understanding of a subject rather than just being able to solve problems. If that sounds like something that interests you and would help you in your journey learning math and machine learning, please feel free to subscribe to my channel down below, as I'll be coming out with a lot more videos like this one. And please let me know if you have any questions or comments on how I explain things. I'm always looking to improve and understand things that I could do better. This video is about Green's theorem. When I was learning this from other sources, there were kind of some things that gave me some hangups, and I had to kind of come up with ways to logic through why things work the way they work myself. So I kind of tried to include those sticky points for me, so hopefully it can help you understand it more quickly. And without further ado, let's get into the video. So the first thing I want to get out of the way, some prerequisite knowledge that you have to understand this, the subject that I'm going to be going over right now. You're going to have to understand line integrals, double integrals, and the 2D curl formula, basically the formula for the 2D curl at any point in a given vector valued function. So here's Green's theorem formally stated. This first side of the equation, what does it mean? This basically means the line integral over the closed curve C, so any closed curve C that's going counterclockwise, in the counterclockwise direction of the vector field F. So it's basically the line integral of the vector field F around this curve C in the counterclockwise direction. Basically, f.dr, the dr is some little increment in our curve, and it's kind of measuring how much the vector field F is kind of helping us along our journey as we go around this curve. Hopefully you understand all that. If you have a conceptual understanding of line integrals, you should. Now onto the other side of the equation is basically equating this line integral around the curve C to the double integral over the region R, which is enclosed inside of that curve C, of the 2D curl at each point. So it's basically taking the 2D curl at every little point inside of R and adding them all up, and that is going to be equivalent to the line integral counterclockwise around the curve C. And you can kind of see how these connect together, because obviously the 2D curl at a point is how much counterclockwise rotation the vector field has. And so it's kind of saying, hey, the curl at every little point is equivalent to the total curl around the perimeter of this region. Obviously that vector field F in this example is going to be in the format of just some vector valued function with a I component that's some function of x and y, and a j component that's some function of x and y. So without further ado, we'll get on to the first section of the proof here. All right, so on to the first part of the proof. As you can see, we're going to start with an example that's kind of a limited version of the kind of total picture here. We're going to find the line integral around the curve C of this more limited vector field P dotted with dr. So as you can see here, the new vector field I've drawn, every vector in P only has an x component, so it only goes side to side, not up and down. And you can see here that's reflected. It only has an I component, which is a function of x and y, and no j component. So the first thing we're kind of going to do here to try and simplify this term and kind of get it into something that's useful for us is to kind of think about what dr is. And you guys should kind of understand this from your prerequisite knowledge of line integrals. But if you can think of dr as a little tiny increment, I'll get a different color here, as a little tiny increment along your curve here, it's going to have some y component and some x component. And so this is dr, and then it's made up of dy and a change in x. So one way to think about that is normally when we're solving for a line integral, we would parameterize this curve C in terms of some parameter t. And so it's simple to kind of express these little changes in R as the change in x with respect to t times the change in t. So for any little change in t, how much is x going to change? And that's all times the I unit vector. And then plus the change in y with respect to t times the change in t times the j unit vector. So if you can kind of see here, and then when we kind of solve this integral with that parameterization, we're going to pull the dt to the outside, and then we can solve a single integral just in terms of t using our parameterization. But for this example, we are not really going to be using a parameterization, but it's just kind of good to kind of conceptualize what this dr is. So we're just going to cancel out these dt's and express it purely as dx times I plus dx times I plus dy times j. So very simple. The change in r around the curve is just the change in x times the the I component plus the change in y times the j component. So then thinking about that and this vector field p right here that we have, there's kind of an easy way we can kind of simplify this integral. And I'm sure you can already kind of see where I'm going with this, but it's going to be the integral around the closed curve C of this function of x, y, which is with the I component, and then that's times dx. And then since there's no j component here, that's going to be it for the integral. So now that we've kind of taken this more abstract integral around the closed curve C and change it into this more simple representation where we're only integrating with respect to x, we can kind of split this integral into two parts at the highest x value and the lowest x value, and just kind of integrate with respect to x twice to get our full integral. So we'll kind of cut off this top part of the curve from the highest to the lowest, and we'll call that C2, which will equal y equals y2 of x. So basically all we did there was we cut off this top part of the curve that goes from the maximum x to the minimum x on the top, and kind of just represented y with respect to x at any point in this curve. So it's just at any point y equals this function y2 of x. And then we will do the same thing with the bottom half. We'll color it in orange here, except that one's going to go from the lower x bound to the higher x bound because it's going counterclockwise again. And that one will be C1, and that will be y equals y1 of x. And we'll go ahead and label these lower and higher bounds. We'll label this lower bound right here A, and we'll label this higher bound here B. And now that we have that, we can rewrite this integral more simply as just two single integrals from either a to b or b to a. So we'll start out here with this top line. So it'll be the integral from, since it's going counterclockwise here, it'll start at b and go to a. So b will be the bottom bound and a will be the top bound of, and so then it'll be p of x, comma, and then y will now be a function of x, so it'll be y2 of x, and then that's all times dx. And then our other integral here for the bottom part of the curve, we will add on to that to get the total integral around this curve, will be the integral from, and then this one goes from a to b when it's going counterclockwise, so we'll put a on the bottom, b on the top, and then it will be the integral of p of x, y1 of x, dx. So hopefully you can understand how I just did that. We kind of just took this kind of more abstract integral around the closed curve, and since it's only kind of caring about the increments with respect to x here and not kind of the whole dr, change in x and change in y, we can kind of just go around, and for every point here we pick out the vector field that's just a component of it in that position that's in the I direction, and multiplying it just by a little increment in x and not y. And then, obviously, since we're going counterclockwise, this one's going to go from b to a on the top and then a to b on the bottom. So now I'm going to do something right here, which I'll kind of explain more in depth at the end as to like why this needed to be done to make everything kind of work out the way it works. But what I'm going to do is I want to switch the bounds of one of these to kind of get them as the same integral so that I can combine them together. So I'm going to go ahead and choose this top curve right here and switch the bounds and have it go from A to B. And then as you guys know, when you swap the bounds of an integral, that's going to flip this whole thing negative right here. And so then in turn, you can kind of rewrite this whole thing as one integral from a to b of p of x y1 of x minus p of x comma y2 of x, and then all of that times dx. So hopefully you can see how I kind of did all that. Obviously, if you add one integral to the other, you can obviously combine them together if it's the same integral. And then this dx I just pulled out because it would have been multiplied by both of them. So it's this entire integral from a to b of the vector field p at x and y1 of x, and then minus the vector field or the x component of the vector field p at x and y2 of x. So now again, this is kind of just so that it gets to the same result that we need to at the end, and I'll go into more depth once we kind of get to our result as to why I need to do this. But what I'm going to do is I'm going to flip this whole thing. I'm going to multiply it by -1 on the outside and -1 on the inside. So that's kind of going to turn this one negative, and then so it's going to be negative y1 and then plus the vector field p at y2. So now, if we kind of see what we have here, we can rewrite this in a way that that kind of makes things interesting. So we will go the negative integral from a to b of, and now we'll just kind of write this more simply, p of x, y, and then we'll put evaluated at y equals y2 of x, and then at the bottom y equals y1 of x, and then times dx. So I hope that you've seen notation like this before. This basically just means evaluated at y equals y2 and then subtract out this evaluated at y equals y1 of x. And now, if you can kind of recognize right here, what we've got is a situation where we can use the fundamental theorem of calculus to rewrite this whole pink term in the middle here. So I'm going to go ahead and restate the fundamental theorem of calculus for you guys, just so you can kind of see the connection here. It basically states that if you have the integral from some bounds a to b of the derivative of a function f with respect to some variable x, it says that is equivalent to that function evaluated at x equals b subtracted from that function evaluated at x equals a. And basically, that's this thing right here is just saying f of b minus f of a. And so you can kind of easily see how we can kind of plug this in here and turn this into a double integral. So let's go ahead and do that right now. This equals negative the integral from a to b, and then on the inside, this pink one will turn into the integral from y2 of x to y1, or from y1 of x to y2 of x of the derivative of the function p with respect to y dy, and then to cap off the original integral, we'll put a dx at the end here. And so you can easily see how we just did that. We took, basically, we kind of went backwards here. We took the function evaluated at 2 points and kind of moved backwards, change it into the integral from one bound to the next of partial p partial y, because this is with respect to y here, obviously, is the variable that's changing, and then dy dx, which came from the original integral. And this totally works since it's a double integral. The bounds on the inner integral can be functions of the outer integral's variable. So if you can see here, we can kind of rewrite this, and I'll kind of go through the details of it in a second, more simply as the negative double integral over the region R of partial p partial y times dA, to kind of simplify things here. And that is the final result that we were looking for in this. And you can easily see how we did this. We can kind of change this more, obviously more precise representation of that integral to just the general integral over the region, because we're kind of going, first of all, from that upper bound to lower bound here. So we're taking this function and integrating down to that function over the y-axis, and then from the maximum or from the minimum a up to the maximum b across the x-axis then. So this right here, specifically with these proper upper bounds on top, the y2 is on top here, so we want to integrate from y1 to y2, and then from a to b equals the double integral over the region R. And then dy dx is obviously can be represented as dA. It's some little piece of area that makes up of a dy and then a dx. And now I'll go over kind of why I made those seemingly arbitrary choices at the beginning, and you can kind of see why that is. We couldn't rewrite this as the double integral over the region more simply if the bounds here were all mixed up. Going from the top bound to the lower bound incorrectly would have flipped the negative sign inaccurately, and we couldn't represent this as the general integral over the region. So up here, first off, we needed to make sure that A was always the bottom bound and B was the upper bound, because A is the lower x value, B is the higher x value. So that's why we kind of flipped this one here and made them into one integral like with this. And then obviously right here, we can't have the y1 bound being treated as the upper bound, or else that would no longer make it the integral over the region either. So we kind of had to flip these around so that the upper bound here is correctly y2 and the lower bound is correctly y1. So I hope that you can see why we kind of needed to make those seemingly arbitrary choices so that it could translate into the general double integral over the region to kind of get to our conclusion here. All right, so here on to our second example. It's going to be very similar to the first with the same curve C, region R inside of the curve, except now we're using a vector field where all the vectors only have j components, so they only go up or down and don't have any x value in them. So I assume after the last one, it'd be pretty simple to figure out that this line integral of the vector field Q around the curve C is going to pretty simply simplify into the line integral around that curve. And then think about it. So this one only has a j component. So when dotted with our dr up here, which has dxi, dyj, we're going to kind of lose that I component because it's got 0 for the I component here. And we're going to just be left with this function Q of xy times dy. And then from there, we're going to start by doing the same thing. Now that it's only in terms of the y component being multiplied by the this q function of our vector field, we're going to simply cut this line at the highest and lowest y values and split it into two lines so that we can integrate separately and then add them together. So we're going to call this top line right here, going counterclockwise, is going to be C2, which is x equals x2 of y. And then this bottom line over here, just going to go counterclockwise this way from top to bottom, is going to be C1, which is x equals x1 of y. So kind of the same thing, except we now split it along the highest and lowest y values and have a top and bottom line on the y-axis, whereas not on the x-axis. And these lines now are functions relating mapping each y value to its respective x on either the top or bottom side. And so now I hope you can see where we're going with this. We're going to do the exact same thing as last time. We're going to rewrite this integral right here into two integrals. So the first one for this top curve is going to be the integral from, let's remember to label our bounds here. We'll label this one B at the top, and we'll label this one A at the bottom. So this top curve is going to go, counterclockwise pointing up. It's going to have A as its lower bound and go to B as its higher bound. And then it's going to be of the function Q, and where the x that's plugged into that function is x2 of y for every y value. And then you're going to plug y in as well. And then this is all going to be times dy. And then for this bottom curve, we're going to add on the integral from, counterclockwise, we're going from b as the lower bound towards a as the upper bound. So we're going to put b on the bottom, a on the top of the q function where the x we plug in is x1 of y, and then we'll plug in y, all times dy. So now, as you could probably figure from our last example, if we want to relate this to the area within the region, we need both of these to be integrating from the higher y bound to the lower y bound. So this one's already good. It's already kind of starting at the lower bound, going up to the higher one. That's fine. But this one right here kind of needs to be flipped, or else we would kind of result in the negative area at the end once we relate it to the area of the region. So we're going to go ahead and swap the bounds on this one to make it the same as the yellow one. So it's going to go from a to b. And then obviously when we swap that, it's going to flip the sign of this integral negative. So turn this to a minus, and this statement is still equivalent. Now, as we saw last time, we'll just simply rewrite this as one integral from a to b. And then in that integral, we will have q of x2 of y and y minus q of x1 of y and y. And then all of that times the dy, the change in y. And if you'll notice here, this one, unlike the other one, already has the x2, which is kind of the higher curve here on the x-axis, as the upper top bound, and the lower one here that's being subtracted out is already x1. So this is good. We don't need to flip the sign of the whole thing negative. We will just move straight on to the next step, where we write it as the integral from a to b of, and we'll just say generally the function q of x, y, and then evaluate it at x equals x2 of y, and then x equals x1 of y, and then all that times dy. And then same thing as last time, we'll rewrite this as the integral from a to b, and then on the inside, we'll have the integral from x1 of y to x2 of y. So these are all, wait, let me redo that, x2 of y. So these are just functions of y, basically, on the inner, and that'll be of. So just like before, we'll use the fundamental theorem of calculus here. We had this. We will go back to change it into an integral form here. So basically, since these are some x values here, we will change it to partial q partial x times dx, and then dy. And then, just like last time, you'll notice here we have, for the x-axis, we're integrating from the upper curve, or from the lower curve to the upper curve correctly here. And then on the y-axis, we're integrating from the lower bound a to the upper bound correctly here. So this whole thing is able to be rewritten as the double integral over the region R of partial q partial x, and then times dA. We can rewrite this dx dy as just some little unit of area in our region, dA, dx times dy. And so that is kind of the result we were looking for on this second one. And now, in a moment here, I'm going to put these two together and kind of show you how we get to Green's theorem from here. So I've got a new page here where I kind of wrote down the results of the two exercises we just went through right here. So first, we found that the integral around the closed curve C of this p component times dx is just equivalent to the negative of the double integral over the region of the partial of p with respect to y times dA, which is these little increments of area in the region. And the same thing goes over here, around the counterclockwise curve C of this q function times dy. It's going to be equivalent to the double integral over the region R of the partial of q with respect to x. And kind of the reason this one turned up negative and the other one didn't is just an attribute of the counterclockwise rotation here. You can see here, for the y example, the top curve here was already going from the bottom bound A to the top bound B just by design of the counterclockwise curve. Whereas in this one, the top bound was already going from the top bound to the lower bound incorrectly and then needed to be swapped upwards, which kind of is what caused this whole thing to be needing to be flipped negative, which is why it kind of turned out like this. So now we're going to kind of generalize this. In both of these, we had a more limited vector field that only had one component or the other. And now we're going to think about a line integral over a vector field that has a p component, which is a function of x and y, times I, so that's the I component, and a q function, x and y, which gives it a j component. So now it's a more general vector field where the vectors are going to be pointing in every which direction. And so if we think about it, that line integral over the closed curve C, we're trying to find f dot dr. But what was dr? As we kind of talked about up here, dr is kind of this little increment around the curve. And we thought about it as dx times the I component, so kind of the change in x times the I component, and the change in y times the j component. So what happens when we dot that with this vector field here? We will rewrite our integral as the integral over the curve C, and now we have two components, so it's p of x, y times dx, and then we will add to that q of x, y, and then dy. And now all we have to do to kind of get to our Green's theorem solution from this one integral that we're looking at, this line integral around the curve, is kind of split those up into two separate integrals around the curve C. So first we'd have p of x, y, dx. And then we just add integral around C of q x, y, dy. And now you can pretty easily see how we can take this and kind of use these two things that we found here to get to our solution. So what is that going to equal? We'll start a new line here. This first term right here, we'll do it in green, is going to equal this business right here. So it'll be like that, negative double integral over r of the p dy dA. And then this other one over here, we'll do in red, will equal this business right here. So we'll add double integral over r of the partial q partial x dA. And then we just combine those together and we have our result. So we have the double integral over r. And then inside of here, we're going to have, let's go ahead and start with this one because it's positive, partial q, partial x. And then we will subtract, because this one's negative, partial p, partial y, and then dA. And if you notice, now we have stated Green's theorem here. We have started with this general line integral of the vector field f around the curve, counterclockwise curve C, and we have found that it is equivalent to the double integral over the region that it encloses of this 2D curl formula that you guys should know at every given point in that region. Add it up. So there you have it. So now you can kind of see here why people kind of refer to Green's theorem as the fundamental theorem of calculus for multivariable calculus. Just as this one, it's kind of saying right here, what is this saying, right? Inside of here, you have kind of the change in f as x changes. From x will go from a to b. So it's kind of saying adding up all those little changes from a to b is equivalent to just taking the original function at a and b and subtracting them out to get the total change over that period between a and b. And it's kind of similar here. It's kind of saying that, you know, if you want to know the total curl added up at every little tiny point in this region, you can kind of just take the line integral around the outside of the region with the field going counterclockwise, obviously, and that kind of tells you everything you need to know about the entire region inside of it. So I think that's kind of cool, you know, relating just the perimeter to kind of the entire region as a whole. You can kind of go one way or the other depending on what helps you to solve a specific problem. So the next thing I want to do, now that we've satisfyingly proved Green's theorem here, is deduce the 2D divergence form of Green's theorem from it as well, because it's pretty simple to kind of get the curl version and then kind of go straight to the divergence version and understand how that works. So obviously, when you're looking to find just a normal line integral around a curve, you're taking the vector field f dotted with this dr right here. And remember, we were thinking of dr as some little increment along our curve here, and that consists of an x component and then a y component going up. So little dr is just kind of a vector pointing in the direction as you move from one point to the next around the curve. And that's when you dot it with an f that's pointing whichever direction, it kind of calculates, you know, how much is f helping us around the direction of the curve. It's kind of measuring how fluid flows in this direction around the curve. So to find the divergence or flux through the curve, which kind of represents, like, you know, how much fluid is kind of flowing out of the curve from inside in every direction, you need to dot f with this normal vector pointing outward, an outward normal vector. So from here, instead of having a vector pointing around the curve, you'd want one pointing perpendicular to the curve right here, pointing out, so that when you dot it with f, you kind of see how much the vector field f is sending particles outside through your curve. And basically, the easiest way to do that, we'll write n. If you kind of think about this dr as an x component and a y component, a dx and a dy, how would you, I mean, if your vectors are going counterclockwise, you want to rotate clockwise 90 degrees to get that kind of outward facing normal vector. And then this ds kind of just represents that it's the same magnitude of our dr around here, because this is a unit normal vector, meaning its length is 1. Ds kind of just says it's going to be proportional to the you know, the size of the portion of our curve that we're finding at every given point. So it's pretty simple to rotate a vector 90 degrees clockwise. Pretty simply, we'll just write our little nds as dy I plus, oh, actually, we will go minus dxj. And you can kind of see why that is. I mean, if you took a vector that's pointing up, you have your y component here. To rotate it, you need your y as the positive x. And if you had an x component, it's going to be now pointing down in the y direction with that magnitude. So basically, turning it 90 degrees, you're just going to put the y, whatever was in the y, you're going to point in the x direction, and whatever was in the x direction, you're going to point down in the y direction now. I hope that made sense to you guys. Just try and kind of think through it logically on your own as well. So then, kind of using this representation of our kind of proportional normal vector, so this would be the unit normal and then times ds to make it kind of proportional to our dr, we can kind of simplify this line integral kind of similarly to how we did for the curl version, except now it's a round vector field C, and if you remember, f has a p and a q component, so it's going to be the p component times dy minus our q component times dx. And it's kind of simple to see how we kind of get to our divergence form. So we can kind of relate this here and think about how our curl version kind of shook out. So the curl version, it had a p some function times a dx plus some function times a dy. And that function that was multiplied with the dy, it takes a positive partial of that with respect to x. And then the function that was with the dx, it's negative the partial of that function with respect to y. So let's see, how can we rewrite this one in the same kind of manner here? It'll be double integral with respect to r, which is this region right here. And then, so we'll start with this thing with the dx next to it. The function is negative q right here. So what happened to the dx function? It was flipped negative, and it was the partial of that function with respect to y. So the first term here is going to be the negative of this, so it's just positive partial q with respect to y. And then what happened to our dy, our function that was tied to dy? We're using the same formula that we found with the curl version of Green's theorem. This function, it's just left positive and the derivative taken with respect to x. So p plus partial p partial x, and then dA. So we've just used the formula that we've already proven here to find the 2D divergence / flux form of Green's theorem. So that basically says, right here we kind of flipped them, but it's basically saying the line integral around this line of these normal vectors, kind of outward pointing normal vectors, the line integral of all those, which is basically saying the flux through the curve, going out through the curve of the vector field f, is equivalent to the 2D divergence, or the divergence at each individual point around R added up. And there you have it. All right, I'm going to go through one more example, which is going to kind of hopefully solidify your conceptual understanding of why Green's theorem works the way it works, why the line integral around some curve in a counterclockwise manner, or the flux out of that curve, would be equivalent to the divergence or curl at each infinitesimally small point within that region added up. Kind of see that relation between inside a region and outside the curve when it comes to curl and divergence. So for this example, you're going to need to understand the formal definition of 2D curl. Now, this is kind of a hairy expression, so I'll do my best to explain it intuitively so you kind of get at least what this is trying to say. So think of AXY. I mean, obviously, a curl at one point is going to only refer to one little point in space, right? Or one point, and we're calling that XY here. So it's a curl around Y, or at the point Y. So this kind of AXY refers to just some area around XY, and that going towards 0 is kind of just like saying, hey, this curve around XY is going to shrink so that the area inside of it becomes as close to 0 as possible, towards 0. So it's the limit as this curve shrinks and shrinks towards that point of kind of this line integral around that curve of the vector field f, dr. You've kind of seen a term like this, just kind of calculating this line integral around the curve. But since obviously, if you're adding up all the little points here dotted with the vectors in the field f, this kind of line integral is going to be able to be a bigger and bigger value proportional to how big the actual curve is. So as it kind of shrinks, we want to find just the raw curl, which is regardless average curl over the area. So we're going to basically divide by the area of how big this is to kind of just get the average curl rather than the total curl. So it's kind of just saying what's the average curl around this line as this line shrinks and shrinks towards the point xy. So it's kind of got the limit as it gets smaller and smaller. So once it gets really, really small, it's a tiny little curve going around that point, and we're taking the average curl, which is just the line integral with the vector field f around that point going counterclockwise. Hopefully that made a little bit of sense to you. I'll leave that up there at the top so we can kind of use it later for this kind of more intuitive explanation here. I will say the most compelling argument to me is not going to take any arithmetic or manipulation. I'm just going to tell you this first thing. So imagine we have this curve C right here, and we're going kind of counterclockwise around it. So I'm kind of just trying to draw some kind of direction here. And if we kind of take the line integral with some vector field f, we're going to take all of these little vectors right here going around it and dot it with f and kind of add up all those solutions to kind of get the line integral around this curve. Now think about kind of chopping this curve into kind of 4 little sections here, right? And we could call this C1, C2, C3, C4. If you'll notice here, if you go counterclockwise around all these, you'll see this one kind of goes up, then over, and then over here. This one goes up here, and then down, and then over here. This one will go this way, and then over, and then down. And then this one will go up, over, and then over this way. And so you'll kind of see here that since these four separate curves here kind of share a boundary line at these points, and if they're going in the same counterclockwise direction, the vectors that you dot with the field f for this curve will be pointed up, and the vectors that you dot with the field f for this curve over here will be the exact opposite of those. It'll along the same line except pointed directly in the opposite direction as the first one. So if you can kind of think of it here, if we add up the line integrals around all these curves, these little bits here in the middle will cancel out because the vectors will result in the exact negatives dot products of each other with the vector field f. And the kind of the same thing goes for flux. If you're thinking of outward pointing normal vectors, this one would have an outward vector going that way, and this one would have one going this way. So when you dot both of those with the same f, you're going to get positive, negative, and they're going to cancel out to 0 in here. So for both divergence and curl, if you chop this up into multiple pieces, you're only going to keep these outer line integrals, and these middle ones are going to all cancel out here. So that kind of makes sense if you start chopping this up into infinitely small pieces, how you're still only going to end up with the result of these lines around the perimeter out here, and the middle lines are kind of all going to just cancel out in between each other because they're kind of pointing exactly opposite to each other. So that really made a lot of sense to me when thinking about why the outer line integral around there would be the same as adding up all these infinitely small curls and divergences within the region. So now this little exercise I'm going to go through here is just going to kind of a little bit more formally relate this little example I just gave you to the formal definition of Green's theorem. We're going to start out with just kind of thinking of this integral again, c of f dotted with dr. And now, just like this example I've shown you, we have just found that that is equivalent to the sum from k equals 1 to n. And k is just going to be the label for, like, say this curve is c1, and this one is c2, and this one is c3. It's just going to be however many pieces that we chop. N is going to be the total number of pieces that we've chopped up our region into. And then it's going to be the sum of those line integrals around ck. So c sub k is just referring to which one of these pieces, and we're going to add all of these line integrals up, of f dot dr. So that's pretty simple. This is basically just kind of formally stating with an equal sign kind of what I just said. If we kind of cut this up, these are going to cancel out here, and we can kind of write out that observation like this. We can kind of think of the formal definition of curl at each one of these points as obviously this line integral around the smaller and smaller little curves that we get as we cut this into infinitely small pieces, divided by the actual area in the middle of that tiny little curve that we have. So if we think about it here, the formal definition of curl is approximately this as it goes to 0, this bit over here without the limit, just around all these tiny little sections we're making as we cut up this infinitely. We can kind of think of this here as the 2D curl times the area, because we're kind of keeping that area element here. This is kind of just minus this. So we can see this is the 2D curl around our very small ck curve that we've got by chopping this up, just times the actual magnitude. So we can rewrite this as the sum from k equals 1 to n of the 2D curl of f at that point times the area of rk. And rk right here is just going to represent the area within our small curve ck. So you can kind of see how we got from this is the formal definition of curl. It's just that times that actual area r is our approximation of and actually, yes, it's more accurate to represent this as an approximation instead of an equivalence, because still this isn't infinitely small, so it's just very, very close to what the 2D curl would be, since it's not the limit as it approaches 0. It's just some very, very small area. over there that goes around each individual point, because as we cut this up. So then from there, you can kind of see how we got to Green's theorem, because this sum over here, if we change this sum that we're taking into a double integral, we will then get the limit as we approach zero, those infinitesimally small little points within the region R. So now that we have this approximation here, as we get smaller and smaller slices, smaller and smaller CKs, and we add them all up, and we've addressed that that is equivalent to our line integral around this curve, we can kind of look at this and think about something real quick. This can kind of be turned into a double integral over the region R, because we're adding up over every little small bit of area, which can be thought of as little dAs, little small sections of area, and we're adding up the curl within that area, proportionate to how big that area is. I hope you're following along here. So we can rewrite that as the double integral over R, our region, of 2D curl of f times dA. And now we're able to kind of get rid of that little approximation, because what a integral does at heart is that it takes those infinitesimally small little areas, and so it's no longer just an approximation of we cut it up into some arbitrary amount of sections. The integral actually takes every infinitely small section and adds them up for us, so we can kind of remove this little approximation thing and say that this is totally equivalent. And that actually kind of proves what the 2D curl formula is, because obviously probably when you learn 2D curl and divergence in your calculus class, they just kind of told you the formula and intuitively told you why it works that way. But now we've proven Green's theorem to be this, and so if now we've proven here that this actually equals the 2D curl of f for at each little dA, each little point in here, that actually proves that if this equals that and this also equals that, then this right here must be the 2D curl formula, must be the actual 2D curl formula, because I'm using this kind of formal definition for curl that we were looking for right here. So it kind of connects everything together really well there. And you can kind of think of this would translate exactly the same to the divergence version. Just like I said, kind of thinking of those outward facing normal vectors here, we would just change it to f dot, just like up here, this unit normal vector times ds, and we could write down the formal divergence formula definition and have the exact same kind of process here, except for divergence. So I encourage you to kind of go through that yourself, but you know, it's pretty simple. It's the exact same steps for divergence, and you can kind of prove it the same way. I guess that's it for this section. Thanks. So the last thing I want to do is kind of recap everything that we went over here. Hopefully we've got a great understanding of Green's theorem and how it relates to curl and divergence. So we started out with just listing our prerequisites and kind of showing what we needed to prove here. We went through this example where all of the vectors only pointed in the x direction and kind of proved that with just this, our simple line integral with just x components turns into this double integral over the region R, the negative of it, of the partial p with respect to y. And then we did the same thing for this vector field with only j components, and then we kind of combine those together to get to our Green's theorem. And I hope that you guys really understood kind of why the counterclockwise rotation translated exactly to these steps that we needed to do and how that makes sense. Then lastly, we've derived the 2D divergence / flux form of Green's theorem from the regular curl circulation form that we already had before, kind of figuring out what these unit n.ds vectors are that we need to dot it with, and then kind of showing how you can kind of use Green's theorem to get to this 2D divergence formula result. And then at this part here, I just kind of want to walk through the steps that we did. We listed the curl formal definition, which basically just says if you take some line integral around a point, which is infinitely shrinking towards that point, and take the average curl, or the average kind of force in that vector field that goes around that curve, again, as that line integral, as the area within it kind of closes around that point, getting smaller and smaller, what is the average curl around that line, or average of this line integral kind of proportional to the area of it. Then we kind of walk through this example where if we cut up this curve, how taking the line integrals around all these individual ones, they would kind of cancel out at these shared lines that they share in the middle. And then we kind of represented that as a sum now of the line integrals around all of these subcurls here, or subcurves. And then we were able to show how that's approximately equal to the 2D curl of each one times their area, all added up. But obviously, since their area is a bit bigger than 0, it's not infinitely small, we can't call it an equivalence. It has to be a approximation, because we're obviously using bigger areas than we'd like, because we can only cut it into so many arbitrary sections. And then knowing that to make it an equivalence, we needed to add up all the infinitely small sections. We have a tool that does that perfectly for us. As we learned integrals, we get all those infinitely small dAs across the whole region, and now we can say that it is equivalent to the 2D curl formula added up at each point over that region, and prove that 2D curl must actually equal this formula that we've learned earlier on in our multivariable calculus classes. I really hope all that made sense to you, and try and work out how this last example would work the exact same way for divergence. I think it's really good for like strengthening your understanding of how everything works and feeling really good about your conceptual grasp on things. So thanks, guys. Until next time.